Welcome, everyone. Today, we're going to talk about private LTE integration with some applications on a project that Anterix and NREL partnered together for the past 2 years or so. My name is Jim Lee. I am a manager of engineering solutions. I've been working in industry comms-wise about 20 years. With Anterix, I've been supporting solutions and systems architecture, design, operations, and deployment of various systems, proof of concepts, trials, and also looking at various end-to-end applications that a utility or critical infrastructure might be using. So I'll be presenting some of the results on the slide. We also have Dr. Barry Mather here, and I'll hand it over to him for his introduction.
Yeah, thank you, Jim. Good day, everyone. My name is Barry Mather. I'm a group manager and researcher at the National Renewable Energy Lab. My background is in sort of all things related to specifically distributed energy resource integration into the grid, specifically PV systems, and other renewable sources of energy. I'm very fortunate to lead a group of researchers in this general area and also lead projects myself. To start off with the presentation here today, we'd like to share a video that the project team put together, kind of summarizing and giving you a general taste for the overall project before we provide some more details during the rest of the presentation. So please enjoy the video.
So NREL and Anterix are collaborating together in order to create a framework in order to evaluate communication in advanced distribution management system applications. Not only are we able to create a framework, but we're also able to evaluate certain scenarios with different congestion in order to see how well the wireless communication performs. We think that this can have a huge impact on utilities and how they view communication across the grid.
Anterix brought in a 900 megahertz private LTE system that we deployed in the lab to serve as the communication link between the devices in the lab and the control systems. In this case, the Advanced Distribution Management System.
Having the Energy Systems Integration Facility, a place where we can test these communication protocols with the devices that we've characterized and understand, will provide that success and impact for the future.
By testing it here, evaluating it here, we're able to answer questions on its performance before it goes out into the field where utility will actually implement a wireless system.
We're really on the cusp of doing something new and great in building this future grid that we've been envisioning for the last decade. And this future grid is decentralized. It's built with many assets spread across the whole distribution system as opposed to one centralized location. And for that, probably one of the most important things that we're going to need is communications.
We thought it was critically important to come and collaborate with NREL because of their world-class facilities for testing and developing renewable energy technologies. Without NREL, we wouldn't have been able to test out direct transfer trip functionality over wireless.
The goal of the project really is to allow utilities to ask usually the second question that comes up when they're looking at implementing an ADMS system. The first is, how will the ADMS system really benefit my overall operations in my system? The second is, how do I actually implement it?
As a IAB member, it's very important for us to sit at the table with these ideas and let these researchers know early on whether or not this is actually attainable, whether or not we can take this idea and push it out to the grid edge and really get some economics out of it for a utility that's going to help our membership.
The grid, as everybody knows that's involved in this, the grid's changing. I mean, we were built as a one-way distribution system. We generate electricity, we transmit electricity, and we distribute electricity. Now with the coming of distributed energy, solar and wind, we've got little bitty generation and transmission pockets all over our system. Now we've got a new dynamic, and the ADMS helps us control that and make sure that we have electricity on demand.
We're really at the heart of distribution system grid edge, and as we start to grow more and more of these homes, these assets together, how do hundreds of thousands of devices start to communicate together? Because that's what it's going to take to have a very secure energy future.
Okay, well, that video hopefully gives you a good idea in a short period of time of kind of the overall scope of the project. What I wanted to focus on here just to begin with is really kind of the reason that we're pursuing this project together and what makes it so interesting. As I mentioned before, I work a lot on distributed energy resources and really on the grid integration side of renewables. And of course, that's a big part of overall grid modernization efforts. Being pursued by utilities and of course also the Department of Energy, really everyone within the U.S. Utility industry. If we look at a lot of these different applications, for instance, distribution automation, advanced metering infrastructure, advanced control like conservation voltage reduction, distributed energy resource management systems, and kind of the whole enchilada, the advanced distribution management system. What we see here, right, is a lot of control and monitoring, sensing capabilities that will lead to obviously much more efficient, optimized, safer, more resilient grid operation. And that's of course what we're shooting for, right? That's the end goal, is to enable these sorts of applications in a real way. In order to do this and really look at how a lot of these applications can really be used, NREL has what's called the Advanced Distribution Management System testbed. This is a system where an actual ADMS system can be installed. It can control real endpoints within a distribution system. The distribution system is modeled via a digital real-time simulator. So we're really doing what we call power, hardware, and loop experimentation of a utility system, but the ADMS effectively is controlling what is, a system that's actually in our lab, of course, not an actual utility system, but it allows utilities and researchers alike to really look at how ADMS systems operate, how they can benefit, which applications within an ADMS system are most appropriate for different regions of the United States, different types of circuits, different types of equipment that are out in the system. And anyway, it's a very useful system for basically de-risking and better understanding the investment that really has to come, the investment and benefit that has to come via an ADMS installation within a given utility. Here's a kind of a complicated diagram of one of the ADMS, we call them use cases, but basically it's a case that's looked at specifically for research and for utility insight purposes, that is controlling a number of PV systems. These would be rooftop solar systems, for instance, in a neighborhood. Maybe there's also an electric vehicle charger. There's some home energy storage, home level energy storage components, that sort of thing. And the real thing I want people to take away from this, right, is that communications is playing a very major part, obviously, in all of these applications. And that's really where this project with Anterix and NREL collaborating really comes from and is focused on. If we look at kind of the darker blue lines within this diagram, you can see they're kind of spaghettied all over the place. And this is, of course, the comms, right, where the ADMS, the Advanced Distribution Management System, sends out control set points, for instance, to dispatch photovoltaic systems up or down, or at least dispatch the maximum amount of generation that they could provide at any given time. In order to make the grid more efficient and allow even more photovoltaic energy to be hosted on the grid or installed on the grid. But the real point is, again, that this communications is certainly an enabler of all these sorts of applications. And oftentimes, although the applications are, there's a lot of attention being paid to the different applications being developed for ADMS, the way you actually implement them and the way communications performance actually impacts those applications isn't oftentimes as recognized or as looked at as often. And that is exactly what this project, its main goal is. This project, just kind of as an aside, is actually designated as a high impact project for the Energy System Integration Facility. That's the user facility lab here at the National Renewable Energy Lab. And this designation comes from DOE, and what it really means is that we're building out a general capability to look at these sorts of concerns. Basically, how does communications performance impact distribution control? So we're really looking to support communications of any sort of type, right? Obviously, utilities are looking at all sorts of different, both wired and wireless types of applications. The other thing that, of course, is very important is we're looking at utility resilience. And when we add an ADMS control layer, right, we may get much improved operations. But if the communications infrastructure, for instance, is fragile, right, is not resilient itself, that calls into question whether that the overall grid will become less resilient, right? So we are really looking for that resilience aspect of, you know, we're looking for comm technologies that work under harsh conditions, work under non-ideal conditions, you know, storm scenarios, that sort of thing. So those are two important points of guidance directly from the Department of Energy, really driving this project. And again, it being a high impact project, we're taking these into careful account as we go. If we look at the objectives for this project, you know, we're starting out really trying to baseline some of the impacts that we see on different communications enabled control functions that the utilities might be interested in. So not only are we building out the capabilities at the Energy System Integration Facility to you know, baseline communications performance, simple things like latency of a command being sent to a piece of equipment, you know, the general bandwidth being supported, again, per piece of equipment or per group of equipment, that sort of thing. But we're also looking to quantify and understand, you know, again, those overall impacts. Specifically on this project, we're looking at a private LTE system, 4G system, which Jim will talk a little bit more about here as well. But of course, the private system allows a couple advantages. You know, makes it a very interesting case. We can prioritize different types of communication. That's a very important thing. As well as it just being a wireless system, right? It looks very advantageous in terms of integrating many of the utility communication systems that exist today and exist, you know, potentially in the future into kind of one common system, right? Instead of having an individual communication system for every type of utility application, there's a lot of evidence showing that, you know, a lot more benefit could be gained and be much more efficient from a cost perspective and even operations perspective to integrate those all into kind of one communication medium, I should say. You'll see more of this later in the presentation as well, but the cases we're specifically looking at within this project there's really two cases. One is a direct transfer trip signaling of a photovoltaic inverter. This is representative of very low, it requires low latency, has to happen very quickly. It's a protective type function. And it's the type of function that oftentimes, you know, is more or less thought that you cannot do this via a wireless system, right? So we're really trying to baseline what is the best possible performance we could get out of the wireless system. This is the lowest latency type function that we could really look at. The other demonstration we're also including in this project is really getting more back straight towards ADMS operations. So it's really a grid control case where we're trying to regulate the voltage, for instance, on a distribution circuit, you know, using multiple elements, PV inverters, voltage regulators, capacitors, that sort of stuff. You know, and again, what are the communication requirements going to that sort of equipment, and how does that impact the ability to actually regulate voltage on the system? This is a slide that just tries to delve a little bit into, again, I mentioned the 4G LTE system, private LTE. Specifically, we're looking at 900 megahertz LTE, as you can see. Again, the idea is that we're really trying to roll up multiple types of utility communications, right? That may or may not be handled currently in different communication channels. So obviously ADMS is a big focus, but you know, you could imagine a lot of other things integrating in here. Outage management systems, distributed automation, all this stuff that I really talked about on one of the beginning slides after the video. Again, it's that integration into a single channel, and again, that prioritization that's possible because it's a private LTE system allows different priorities to be assigned to these types of traffic, and has certain advantages you'll see here in a little bit. We are very fortunate to have a very strong industrial advisory board on this project. I find it particularly exciting because this industrial advisory board is really comprised of a number of utilities that NREL has worked with a good number of times, but also an equal number of utilities that we haven't worked with, on multiple projects. You can see by the list of the utilities here, there's some very large utilities, some smaller utilities, but I think it really just goes to demonstrate that there is a lot of interest in how do you actually implement some of these ADMS systems, and what other pieces of infrastructure do you need to really enable those, i.e. the comm system. What comm systems do I actually need to be looking at? So again, we're very fortunate to have a lot of input on the appropriateness of the use cases that we're looking at, what other applications for this integration of comms altogether, what sort of bandwidths would we be looking at if we're actually looking at handling, say, all utility comms needs, or at least the vast majority, via a single communication system. So again, this industrial advisory board has been very helpful and useful, and we appreciate their support. And this is my last slide that I'll be talking about today, but it's really just trying to point out how we're leveraging a lot of the capabilities already in the energy system integration facility here at NREL. I mentioned before that we have the ADMS testbed. We are leveraging that to a high degree. The idea is not to duplicate that by any means, but really to add the ability to adjust, to evaluate the performance of an overall ADMS system, including the communications requirements, or including communications limitations, for instance. We also at the lab have a number of grid edge devices, of course, that are being used with our tests. Things like distributed energy resources, automatic voltage regulator components. You'll see an example of a breaker that is used as a proxy for a recloser, for instance, out on a line. And of course, we're also using a good number of real-time simulation tools for that power hardware loop simulation that I mentioned earlier, specifically for the ADMS case that we're looking at, using tools like OPAL-RT, etc. So at this point, I'd like to hand the presentation over to Jim to go through some of the specifics and talk about private LTE a little bit more.
Thank you, Barry. Thank you. That was very enlightening on my part, even when you talked about these items and these applications to me, maybe about a year and a half ago, when we started venturing down this road on this project. The fact that a lot of ADMS, DERMS, or even DA applications from a field area network perspective needs comms is something that we ought to look at, right? Based on feedback we get from the IAB members, the Industrial Advisory Board members, both utilities and industry consultants that are out there. So bringing back to the point of one of the first things we talked about is we were looking at testing the enabler of comms. In this case is a wireless broadband technology we're using called LTE, right? So there's a lot of reasons. There's a lot of different technologies out there. One of the bigger reasons we chose LTE as the initial view before we go into maybe the future states of this project, perhaps 5G and beyond, right? Is that LTE has several benefits, right? It is, like you said, it's a technology that can enable low latency and high capacity. It's a broadband technology, right? So it can enable latencies in the sub 20 milliseconds arena, right? Thereby, having pretty quick response. It's a very robust wireless technology, meaning that once you have a area that is covered by one of these LTE towers, covered meaning that for your field area network of endpoints and sensors and voltage regulators and cap bank capacitors, whatever the utilities needs are, the coverage is pretty expansive, right? And pretty robust. Robust in terms of if you have one of these endpoints close to your cell site, for example, where you expect to get good signal quality and strong signal strength, compare that to a endpoint that might be a little bit further out, a mile or 2 mile away from the cell site, where the signal quality is weaker, the signal strength is also weaker. LTE was designed in mind to keep consistent behavior and performance. Yeah, you'll suffer a little bit of the latency because your signal is a little weaker, but we're still talking about tens of milliseconds of latency. And of course, on the bandwidth side, compared to other narrowband mesh technologies, we're talking about LTE speeds here. If anybody has an iPhone or a Samsung Galaxy phone or some other consumer device, that you're able to watch YouTube videos with ease on these devices. So the same concept goes along when we talk about private LTE, right? We want to utilize that capacity, the capability, that broadband performance that's offered by LTE. The other reasons are LTE is a technology that's been around for about 10 years, right? It started off with consumers. Very recently, the technology has evolved into a state where we can use multiple carriers, thousands of devices and infrastructure availability from the ecosystem front, right? So stuff that's off the shelf, we can pull and implement, LTE with. A final reason why we chose LTE, just another reason, not a final reason, is that it can enable resilient applications. In itself is resilient. Applications, because of its broadband capabilities and its secured robustness built into the ecosystem itself, we can enable applications that we wouldn't think about enabling before, especially in the utilities arena and their play, right? So one of the applications, in fact, that we talk about is protection application, transfer trip of a recloser in a lab setting, obviously, in this, but to think about being able to actually enable that resilient application, use of LTE was possible, right? It was the only thing that was possible. One other thing I also wanted to mention, LTE is definitely a data-centric, packet-style type end-to-end air interface, meaning that it is IP-based. So, this is, again, why there's such a large ecosystem of data devices out there that support LTE. Not only does it support it on the air interface and the physical layer, because of its IP-centric packet approach, you're able to integrate a lot of legacy protocols or endpoints that have legacy protocols that were serial. For instance, now you can run DNP3 over IP or DNP3 over TCP IP. You can run Modbus. A lot of the old serial legacy existing protocols can now be scaled to use over LTE. All right, let's just dive right into it. So as Barry mentioned, working together with NREL and the IAB members, we came up with several use cases on the field area network side that we wanted to do. One was this direct transfer trip application, and the other one is the ADMS, which I'll talk about in the next few slides. Now, what makes the presentation or demonstration of this application special is that when we use LTE, we're talking about a private version of LTE for this network. This means that if I was a utility or a critical infrastructure company and I have my own LTE, meaning that I owned not only the devices that attach to this network, the LTE network, but also the LTE networks itself. I own the eNoD, and I also own the core, which means now I have full visibility into every network element end to end, from my data center all the way to my field office, all the way out to each endpoint. I have full visibility of what's happening to my nodes everywhere within my network. I also have full control of my network, meaning that because it's my own version of LTE, and really, literally my own version, I can now configure various things that can optimize my applications. So for instance, in direct transfer application, we know for good reason, this has to happen, the action itself has to happen relatively low latency, relatively quick, and it has to happen. Meaning that we need to be able to prioritize the traffic, the command, and the telemetry for this direct transfer trip to be pretty high on the pyramid. So this is why you see on this chart here, a pyramid here. So the pyramid is really meant to say that if I have an LTE network and it's my own private LTE network, I can configure different lanes of traffic priority for different types of applications. So as an example, and what we implemented here, we basically have configured the highest priority level for the direct transfer trip command and telemetry. We also configured other traffic, part of this field area network that a utility might own, other SCADAs, systems, bank capacitors, voltage regulators, other sensors within their network to be medium priority traffic. And then we also configured what we call other traffic that might be running on the network, such as a video camera, a surveillance camera, that we're just going to consider as low priority traffic for the sake of this demonstration here. And in order to do that, and by doing that, we effectively have configured a comm system that enabled direct transfer trip application, because in the most extraordinary conditions, right, whether it's fully congested, whether my signal is a little bit weaker than it should be, as long as I design my LTE system properly, that signal for direct transfer trip, because I have the ability to fully configure the air interface parameters of LTE, I basically prioritize that traffic as a highest here. So just a little bit more description. The diagram, the schematic that you see here on the right-hand side, basically it shows the portion here, the gray portion, private LTE 900 megahertz system being implemented in their lab, and I'll show you a physical picture of that on the next slide, being connected to a test system. The OPLRT is a test system and measurement system that we used for this experiment. And on the bottom of this is where the end device, the field device, is connected to a recloser, which then is in turn connected to a PV inverter system, and of course, a simulation of load within the NREL lab, that whole setup there. So the objective of this was to be able to always resiliently send direct transfer trip signal to the recloser under highly congested scenarios and under even weaker LTE signal scenarios. And the way to do it is with private LTE. So let me explain a little bit more description on this next slide here of what that actually meant, right? So in the lab, what we basically had, if you look from left to right here, all the equipment that was in play on the schematic on the slide before. Left side here, you basically see the four antennas that was mounted on a test bench within the NREL facilities out in Golden, Colorado. The laptop there is the application that was running the direct transfer trip on the server side. Right to the right of that, you see a couple more pictures of the actual endpoints out in the field, for example, that would have this wireless LTE connection to the antennas or to the cell site antennas on the left side. And on the right-hand side of that, you see two more pictures. One is the recloser that we actually were able to send commands to and receive telemetry from. and of course the PV inverter system in the lab out at the ESA facilities, which was under load during this experiment. So very straightforward test, right? We basically send a signal from the data center or the laptop on the right-hand side, send it all the way over the private LTE channel, and get a response with it. And of course, we make measurements on how quickly it happened, performance on throughput, performance on jitter, all the different things you would look for in the wireless arena. And on the application side, we wanted to see how robust the direct transfer trip actually played out. So we've been talking about FANs, right? Field area networks. So imagine an LTE cell site was deployed in this area here. This is just an example area that we've taken on a map. The tower has the antenna that transmits and receives LTE signal, private LTE signal at 900 megahertz, for example. And then you have all of these other endpoints and applications that are out in the field, right? I mean, we've talked about some of them. Fan capacitors. There's also some meter in here, some revenue meters in here, other endpoints, voltage regulators that might be in the field that might be having a wireless link with this private LTE system that this utility owns. The one application here, the one that's circled in blue, is what we simulated in the lab. That's the recloser that's connected to a PV inverter that is also wirelessly connected via private LTE as well. So in the first test case here, as you can see, what we try to do here is we try to flood the entire air interface, the entire broadband channel with all of this traffic, traffic that comes from a mobile data user, maybe a mobile user, and of course, try to load up the channel, take up all its resources, and still try to send the direct transfer trip signal. Now, what we had talked about was in order for that to really work resiliently, we really have to implement a prioritization. In the first experiment here, we don't implement any kind of prioritization. We just use one highway lane, for example, for all the traffic. So imagine yourself on a highway, interstate highway during rush hour, and you're trying to get off the highway. You're going to have to wait till everybody else gets off first before you can get off. And that's exactly what happened in this case when we ran the test. The direct transfer trip action was very erratic in this case because it didn't have prioritization. Sometimes it occurred, sometimes it occurred seconds later, sometimes you didn't get a response back from the server side. So this is an indication of how not to deploy a private LTE network, right? Or maybe if you have a public LTE network, you wouldn't consider deploying direct transfer trip using a public LTE wireless system. Now, if we go on to the next slide here, this is how, when you have full control over your private LTE network and the LTE air interface control, we basically effectively, you can see the blue arrow there, the traffic that needs to go to the recloser here over the wireless air interface, because we have full control and full visibility into the LTE network, we can configure that as a higher priority. So effectively, this would be akin to being on an interstate highway during rush hour, but now you have a carpool lane or a special HOV lane that allows only specific types of traffic through, right? And so that's what we set up here, a higher priority lane for direct transfer trip traffic. And what happens in this case is that because this is private LTE, when we made many tests here, we can see the direct transfer trip traffic go through without fault with high resiliency, and thereby enabling direct transfer trip traffic. We transition to the next slide. We talk about phase 2 of this experiment. So phase 2 is where we want to look at the existing ADMS systems that's being tested out in NREL, being utilized by several utilities, in fact, and to be able to implement private LTE on top of it. And what that really means is two things in this scenario. If you look at this system here, we have ADMS that are communicating with DERMS coordinators. These DERMS management coordinator systems are out in the field, right? And then each of the DERMS coordinator are now sending and communicating set points, for example, to DERS endpoints that are also out in the field. So there's really two test cases we want to look at, in terms of comms. The one on the top, test 3, a broadband link, right? So one of the very simple, straightforward is to replace their existing, fiber or whatever, and use private LTE as backhaul to these DERM coordinators, and then see how this operates performance-wise under load and the congestion and the coverage differential, what have you. That is one test case. We want to be able to see if we can enable private LTE as backhaul for the DERMs. The second test case is the one, test number 4, located on the bottom. Because these DERs are located in the field, and because LTE works great as a field area network, right? It's wireless. It can certainly support signaling, transmission, and reception telemetry commands to DERs endpoints without the use of a DERMS coordinator out in the field. What that really means is, can we architecturally change the setup or the schematic of a DERMS ADMS system, effectively polling or consider pulling the DERMS coordinator function back into the data center of the utility, for example, right? So you can run the DERMS coordinator function, whatever algorithm it needs to run based on ADMS calculations and algorithms, and then communicate directly over the wireless LTE network to each of the DERS endpoints, set point values and telemetry and what have you. That is an interesting view on research phase 2, because if you're able to pull these DERMS coordinators back to the data center, does this mean now you have a cost savings there? You don't have to have another physical field asset that you need to talk to, but in fact, you just utilize LTE network because its ability to cover many, many endpoints out in the field. So that would be a very interesting result once we get to test it and once we get to see what the results are. And as you know, state-of-the-art set points right now, that we're testing, we're talking about 1 second set points in DERS. Now, implementation of private LTE, can we achieve that? Can we go beyond that? Can we have sub 1 second set points? Does it even matter, right, for the ADMS applications that we're thinking about here, in terms of optimization and power system utility and efficiency? So move on to the next slide. Just wanted to summarize. The end goal here is phase 1, enabled a resilient application, with prioritization, because you have full control of private LTE. One other point I didn't really dive into much is that because it's your own LTE system and it's private, you also have full visibility of each of the network nodes and the networking elements that's part of this LTE system, meaning that now you can actually pull telemetry from it, see how much availability you have. Do you meet certain 5-9 criteria for availability? Obviously, another enabler for cybersecurity reasons, right? Having visibility into every one of your network nodes certainly will help support your cybersecurity needs and requirements in that arena. And of course, phase 2, which is ongoing, is to test and integrate an ADMS application along with DERMS applications utilizing private LTE. So that is, hopefully you're able to learn something. If you have any questions, please let me know or Barry know. Or if you have a chance, head out to the NREL facilities out in Golden, Colorado, and you can actually visualize the setup over there. And we'll be happy, someone there will be happy to give you a demonstration over there. Thank you very much.